Hi everyone, hope you are all doing well and safe. Welcome to the practical course of circuit analysis. Here's your lab instructor Nishita Alwas. Agenda of this experiment includes 7 different sections: lab objective, equipment needed for the experimentation, theoretical background, software implementation, results and discussion part, conclusion, and the task assigned. The basic objective of this experiment is to understand the basic concept of Kirchhoff's laws and their implementation on NI Multisim software.
The basic equipment needed for the experimentation is NI Multisim software installed on the personal computer.
So before moving towards the basic concept of Kirchhoff's circuit's law, we have to look at the basic circuit definitions. Firstly, we have node. Node is basically any point in the circuit where two or more circuit elements are connected together. Like if we see in this diagram, resistor 1, 5 ohm resistance basically is connected to 2 ohms resistance. The point from which 5 ohm resistance is connected to 2 ohm resistance is basically called as node. The point where two or more circuit elements are connected. So this is the point where 3 ohms resistance, 2 ohms resistance and 5 ohms resistance are basically connected. So this is called the node. Next element is basically the branch. Branch is a circuit element between two nodes, like as we can see in this circuit diagram, A and B. We have two nodes. So between A and B we have one resistance of 5 ohms. So this is the branch in the circuit. Then we have the terminology of loop. Loop is a collection of branches that form a closed path returning to the same node without going through any other nodes or branches twice. So in the circuit diagram, we have the loop. Firstly, we have the loop from 10 volt battery source, then 5 ohm resistance, then 2 ohms resistance, and then moving towards the source voltage again. This is called the loop in the circuit. There are various relationships among voltages and currents of an electrical circuit. These relationships are determined by Kirchhoff's laws. Kirchhoff's law governs the conservation of charge and energy in electrical circuits and divided into the two laws according to the current and voltages. Kirchhoff's current law is also known as junction rule, and Kirchhoff's voltage law is also known as closed loop rule. In the year 1845, Gustav Kirchhoff, a German scientist, introduces a set of laws which deal with current and voltages in the electric circuits. These laws became central to electrical engineering in 1845. They are generalized from the work of George Ohm and also be derived from Maxwell's equation, but were developed prior to Maxwell's work. Kirchhoff's current law states that the sum of currents entering the node is equal to the sum of currents leaving the node. In other words, the algebraic sum of all the currents entering and leaving the node must be equal to 0, as we can see in the equation number 1. Here are the two currents entering the node are all positive in value, and the two currents leaving the node are all negative in value. That means the total positive and negative currents equals to 0. Means we can say that all positive currents equals to the all negative current. If we take the example of water entering through the pipe for the understanding of Kirchhoff's current law, then in this diagram on the right hand side of this slide we have 4 pipes. Q1 pipe basically shows the entrance of water from it, and we have 3 pipes Q2, Q3, Q4 from which we can be seen the leaving of water. So entering water Q1 equals to the water leaving from Q2, Q3 and Q4. Exactly the same phenomena as we have seen in the Kirchhoff current law. Kirchhoff voltage law states that the sum of voltage rise across any loop is equal to the sum of voltage drops across that loop, as we can see in the equation and the circuit diagram. We have the voltage rise at the battery of the circuit, and in these resistances, means two resistances are connected in the circuit. So in these resistances we have the voltage drop. So the voltage drop in the circuit is exactly equals to the voltage rise. Now here we have some important terminologies related to the Kirchhoff voltage law. As we know, the voltage rise exactly equals to the voltage drop in any electrical circuit. So voltage rise is basically the current enters from negative terminal and leaves from positive terminal. Voltage drop is basically the current enters from positive terminal and leaves from negative terminal. Voltage source is considered as voltage rise and resistors are considered as voltage drops. Here we have the circuit diagram consisting of two resistances and one voltage source for the analysis of Kirchhoff voltage law. Here we have the series circuit for the analysis of KVL and KCL. In series circuit, voltage will be different across each element, but current will remain the same. So if we write the equation of KVL according to this circuit diagram, we will move towards the battery, towards the R2 resistance in the clockwise direction. So across battery, negative positive VDC, so positive VDC. Across resistor, we have the voltage drop in negative, so negative V1. Across R2 resistor, we have negative V2. And this equation equals to 0 value. So if we talk about the voltage across, specific voltage across R1 and R2, then for the analysis of V1 and V2, we will apply the Ohm's law across these resistances. So V1 equals to I1 R1 and V2 equals to I2 R2. As we know that this is the series circuit, so I1 equals to the I2 and I2 equals to the I. So substituting the values of I1 and I2 equals to 0 in the main equation, we will get the equation in this form: 120 volt negative I total current and 10 ohm resistance, negative total current and 50 ohm resistance. And this equation equals to 0 value. After this, I is equals to 120 divided by 10 plus 50 ohm resistances means total resistance. So the current of the circuit, this series circuit, equals to 2 ampere. Then we have V1 equals to I1 R1 means 2 multiplied by 10 and 20 volt. Same case for V2, which is equals to 100 volt. So as we can see that we have the battery of 120 volt and the voltage drop across R1 and R2. So voltage drops V1 equals to 20 and across V2 resistance we have the voltage drop 100. So V1 plus V2 equals to 120 volt, which is exactly the same value of the battery. This is how we can implement the KVL and KCL in the circuit diagram. To test the KVL and KCL algorithm on any simulation software, we have to move towards the NI Multisim. Here is the window of NI Multisim software. So according to our circuit diagram, we have to place two resistances and one voltage source. So moving towards this block, place the resistance of 10 ohms first, then place the basically 50 ohm resistance right there, then move towards the sources block. In sources we have to select the DC power for battery and ground block. Now change the value of battery, as we have 120 volt battery in our circuit diagram. Now it's time to arrange all these components. Select resistor and controller for the movement of any resistance. Arrange all these components. Now our circuit diagram is complete. Next step is basically the measurement of voltage across the series circuit. As we know that in series circuit, if we implement the KVL, then the entering of voltage is exactly equal to the leaving of voltage in any circuit. So here we have the entering of voltage basically equals to 120 degree, and leaving of the voltage is basically across these resistances. So we have to place the multimeter right there for the measurement of voltage across these resistances. So circuit is completed. Now we have to run the simulation diagram and check the voltage across these multimeters or battery sensors. 120 volt, as we have connected the battery of 120 volt. Next measurement is 20 volt. Across this resistor we have the voltage of 20 volt. Means drop across this voltage is 20 volt, and drop across this resistor is 100 volt. Means that 100 volt across this resistance and 20 volt across this resistance. So 100 plus 20 volt equals to 120 volt, which is exactly the value of battery we have connected in our circuit diagram. So now in this question we can calculate the battery voltages and apply the KVL across any circuit. KVL states that the entering voltage is exactly equals to the leaving voltage. So next step is basically the measurement of current across the series resistance. As we know that in series we have equal voltage, so that we have to connect the 1 volt ammeter basically in the series of the circuit. For connection of ammeter in the series of the circuit, we have to remove some connections like this. For example, we have need only basically 1 ammeter in the circuit. So connect this ammeter in a series fashion like this and run our simulation diagram. Click on this and move towards the ammeter, and we have 2 ampere current. As we have seen in our mathematical work, we have the current value of 2 ampere, exactly the same value we have calculated in our mathematical work. So this is how we can implement KVL and KCL in any circuit for the calculation of voltages and current. Here we have the results and discussion part. The current measurement of the series circuit has been presented in this slide. From this slide, the measurement of voltage shows that the voltage entering is exactly equal to the voltage leaving in any circuit. The conclusion of this experiment proves that Kirchhoff's laws are true. The algebraic sum of all voltages in a loop must equal to 0. The algebraic sum of all currents entering and leaving a node must be equal to 0. For the better understanding of Kirchhoff's current law, you have to listen the next session in which we are going to solve parallel circuit according to the mesh analysis, in which we will firstly apply the KVL and then KCL for the better evaluation of any parallel circuit. Tasks assigned for this experiment are listed in this slide. Thank you very much for listening to me.